Good evening, I'm Yvonne, Staff for Science for the Public, and I welcome you to Contemporary Issues and Innovations. Tonight, we get the facts about the rising sea levels, a matter of growing concern for coastal areas around the world. Our guest is Professor Andrew Kemp of Tufts University. Dr. Kemp is an expert on the patterns of sea level change over 2,000 years. He'll be telling us about the patterns and their causes and how the current sea level rise compares to ancient ones. His studies are used by the Intergovernmental Panel on Climate Change and will be important in the international effort to address the problem of rising sea levels. We're very pleased to welcome Dr. Andrew Kemp. Welcome, sir.
Thank you. Well,
you have studied or concentrated on the last 2,000 years. Can you tell us, is the special reason for concentrating on this period of sea level rise and what's involved?
Certainly, my research focuses on trying to understand how and why and where sea levels changed over the past 2,000 years or so. And the reason we're interested in the last 2,000 years principally is because it's a period in Earth's history from which we can extract a lot of very detailed information from geological archives. So it gives us the ability to look for relatively small changes in sea level that may have occurred, sea level changes that were relatively short-lived, maybe they took place over decades to centuries, and we can compare those records to similarly detailed records of temperature variability with confidence that we are looking at changes that took place over the same period of time. The 2,000 years we look at isn't necessarily a good analogue for what may or may not happen in the future, but we can certainly learn a lot about how different processes work by examining this time period.
So it's the accuracy of the geological, though what's available for you, the evidence is particularly good in this period compared to really ancient times.
Yes, we can see things with a level of detail that is much more difficult to achieve the further you go back in Earth's history, though there are periods, earlier periods in Earth's history that one may wish to examine depending on what you're interested in. For example, we can go to a period called the last interglacial, 125,000 years ago, the last time Earth was in a interglacial climate, and we can look at that period, see how high sea level may have gotten then.
In this 2,000 year period, are there interesting sea level periods in that time?
So we know from evidence, for example, from tree rings, that the climate changed in a systematic fashion during the past 2,000 years. So we know, for example, we have a very recent warming of the climate system from instrumental records, weather stations, but also from tree rings and similar proxy records. That was preceded by a period of relatively cool temperatures called the Little Ice Age. And before that, we have a period that is sometimes called the medieval climate anomaly, where there's evidence that, at least in the northern hemisphere, was a period of relative warmth. So we're interested in seeing how sea level responded to those changes during the past 2,000 years as perhaps an example to understand how sea level and temperature are coupled over relatively short time periods, decades to a few centuries.
And how do they connect with, say, a broader climate change?
So the period, those periods we touched upon, the medieval climate on the Little Ice Age, are relatively very short by geological standards. They're intervals that last a couple of hundred years, a few hundred years, very long on a human timescale, but very short on a geological timescale. So when we examine sea level changes over that same period of time, what we see is a level of similarity between them, that when the climate is slightly warmer, sea level rises. As we enter a Little Ice Age, the rate of sea level rise slows down. Maybe even we see a small sea level fall, and then we see this very strong acceleration in the rate of sea level rise as we enter the historic period. And that couples nicely between the temperature records we have and the sea level records that we have.
Those were natural cycles. What made those occur?
There are certainly cycles in Earth's climate history. For example, we have very pronounced large-scale changes on periods of tens to hundreds of thousands of years that take place as Earth moves from glacial to interglacial climate in a very systematic fashion. So 25,000 years or so ago, we were in a period called the last glacial maximum. Considerable amounts of ice on the land in North America and Europe, larger extent of ice in Greenland and in Antarctica, for example. Since that period, we've been in a warming climate as we've come to the present day, and we're now in an interglacial period. So over those very long timescales, there's certainly cyclicity. That cyclicity is driven by orbital changes. On the shorter timescales, for example, the Little Ice Age, these are periods that are nested within those longer cycles and can be caused by things like changes in the amount of volcanism, for example. So large volcanic eruptions have a net cooling on the climate, and we know, for example, the Little Ice Age was preceded by a period of quite sustained volcanic forcing. Obviously, as we enter the late 19th century, early 20th century, we start to see forcing from the emission of carbon dioxide, which results in warming of the climate.
Now, a lot of the climate deniers, climate change deniers, had argued, if presumably are still arguing, that this is part of a natural cycle, that Earth has gone through this over and over again, or there's an orbital change and so on. But scientists are unanimous, as far as I know, that this present cycle is human produced. Tell us about that, if you would.
In the context of sea level change specifically, we know that as we left the last glacial maximum, moved towards an interglacial period, land-based ice melted, that water returned to the ocean, causing sea levels to rise. For example, we removed the large land-based ice sheet that grew on North America. We removed smaller ice sheets in Scandinavia, Northern Europe, small ice caps in locations like Scotland. That water returned to the global ocean, caused sea level to rise. That sea level rise, driven by the return of water to the ocean, ceased to be a major driver of sea level change, probably around 4,000 years ago. Since when, sea level was broadly what it is, a little bit lower than today, but pretty stable. And then what we see from the geological record and instrumental measurements is that around 1850, sea level globally began to rise again sharply. And we know from some of the work that I've been involved in that the modern rate of sea level rise, the rate of sea level rise in the 20th century, was faster than at any time during the preceding 26 centuries at least. So the rate and the amount of sea level rise we've seen since industrialization is unprecedented in the context of the last 2,000 years.
Okay, and apparently this is accelerating. Is that true?
So acceleration, another good reason to study the last 2,000 years is our instrumental measurements of sea level are relatively short. So we measure sea level at the coast using tide gauges. So a tide gauge is an instrument that sits at the coast and it measures the height of the water with some regularity. These instruments are typically, we have data probably on the East Coast going back maybe 100 years in a handful of places, and a little bit longer if you go to Northwest Europe. But pretty short periods of time. Looking at the last 2,000 years gives us a means to kind of extend those tide gauge records back in time and look for changes in rate. And what we see is not only an acceleration, but really an inflection, an elbow in the shape of the sea level curve, where it goes from being relatively flat. We see the sharp uptick in the rate of rise, and certainly acceleration is predicted under many models for the future.
Okay, that's what I wanted to try to get very clear, that this acceleration is demonstrated, that there is very strong evidence for that, and that is different from the patterns of the past. Is that correct, substantially?
Yes, at a global scale, sea level over the past 4,000 years or so was relatively stable, probably even falling a little bit. Since the late 1800s, early 1900s, we see a rapid and sustained and very pronounced increase in the amount and rate of global sea level rise, which is certainly unprecedented. Since land-based ice ceased to melt. As we entered the interglacial.
Right, and so there are some unknowns, presumably. Is this because it's a different kind of a pattern, an anomaly, or something like that? Is that the way to see it? They can't quite predict how fast the acceleration will continue, in other words.
Changes in the future depend very much on the emissions pathway that we follow. Stronger emissions result in more rise and a greater acceleration in rise. Lower emissions scenario, seek to mitigate that.
Okay, so we can have some hope, I suppose. Now, is it true that that rise is not uniform all over the world? Can you explain how that's governed or what pushes that?
So certainly the pattern of sea level rise has a very, very strong geographic expression. It's certainly not the same everywhere. We often talk about, in terms of global mean sea level rise, kind of the average that's taking place around the world. And in many ways, that's a very interesting quantity to estimate and to think about and to talk about, but it's also not a very helpful quantity in many instances, because very few places, if any, will experience the global mean. What we like to talk about is what we call relative sea level. Relative sea level is, as its name suggests, the difference in elevation between the land surface and the adjacent sea surface. And when you think about relative sea level, that's what you're interested in if you live in Boston or Miami or London. For example, you want to know how relative sea level at your location is going to change. And there are many factors that contribute to that at a given location. For example, there is the amount of water in the ocean mass, which we can add mass by melting land-based ice. We can change the volume of the water in the ocean by making it warmer. The water that's already in the ocean expands, takes up more space. The land surface can move up and down in such a fashion as to cause relative sea level rise or relative sea level fall. We can take mass that's already in the ocean and push it to one side of an ocean basin or the other through winds and ocean currents. That makes a difference. And there are a series of local scale factors that work on relatively small spatial scales. For example, compaction of the land, which results in lowering an exaggerated sea level rise.
Oh, I see. Okay, so the big picture is that it's uneven. The other thing is that as the polar caps melt, the Arctic and the Antarctic, I've understood that each of those affects the rise differently, that is, geographically. Can you give us a hint about that?
Sure, it's a fascinating concept. We call it the fingerprint of ice sheet melt. It's work that's been done by several groups, including Jerry Mitrovica's group at Harvard. In essence, when you have water stored on land in the form of ice, it's a highly concentrated chunk of mass on the planet. Because it has mass, through gravity, it holds the ocean close to the ice sheet. When the ice sheet melts and that water returns to the ocean and the mass of the ice sheet is diminished, its ability therefore to hold water close to it is also diminished, and it has the effect that water tends to run away from the melting ice sheet, such that you can get this very strong fingerprint, this spatial expression of melt that varies from place to place, where you might actually see a sea level fall very close to the melting ice sheet. And somewhat counterintuitively, the most rise is experienced at locations relatively far away from the ice sheet.
Right.
So on the east coast of the US, for example, melting of the Greenland ice sheet would cause relative sea level to fall at locations from Nova Scotia northward, for example, and the amount of rise we would experience would become increasingly large as we move away from the Greenland ice sheet, such that there would be more rise in New Jersey than in Boston, and there would be more rise in Florida than there would be in New Jersey. So we have more to worry about on the East Coast if the West Antarctic ice sheet melts than if the Greenland ice sheet melts. Because if West Antarctic melts here on the East Coast, we'd see about 1.2 millimeters of rise for every 1 millimeter of global average sea level rise. So that's certainly something you want to factor in if you're thinking about future changes and how they may vary from place to place. It depends which ice sheet is going to contribute the water in the first place.
Which goes back to your relative point as opposed to the average point. in terms of so there's this distribution of the rise is unequal. We'll come back to that in just a second. But does the geology of the land itself have any effect on the vulnerability of that particular area? For example, on the East Coast, apparently we're quite vulnerable, and do the difference in the geological differences along the East Coast have an effect on the sea level rise?
There are several ways in which we can think about how risk and vulnerability vary along the coast. If we think about in geological terms, one of the big drivers on the East Coast is the ongoing pattern of subsidence. So the East Coast is subsiding as a result of a process called glacial-isostatic adjustment. That is when there used to be this great big ice mass on top of
New York and
Canada, depressed Earth's crust and lifted up an area south of the ice sheet in order to compensate for that.
Right.
When the ice mass was removed, as that material in Earth's mantle tries to make its way back north, causes the coast to sink. So we're sitting on a coastline that is sinking as the sea level is also rising. So we have a double whammy in essence. We're on a landmass that's going down at the same time as the ocean is coming up. So in terms of relative sea level, we have a pronounced rise.
Okay, so that's one thing. And then another thing is that it seems to be, I'm not sure, so the whole East Coast, I was thinking of Florida and its limestone problem as opposed to other areas on the coast, the same coast, that might have a much different rock based. I don't know if that matters in terms of the sea level rise, in terms of making those areas more or less vulnerable.
So certainly a point of concern for Florida specifically is that since it's a carbonate rock, it's made of limestone, it's very porous material, and the porosity of those rocks means that rising sea level ocean water is able to enter the rock, move through the rock with a degree of ease that it doesn't have elsewhere, for example. So one of the concerns that people have in that part of the world is that salt water will contaminate aquifers in Florida, contaminate the fresh water sources we need for drinking and for certain industries, but also that efforts to protect the coast through engineering will be thwarted by the fact that the water can just move through the porous limestone and get around
That's right.
obstacles
Couldn't care
on
less about walls. Right. Okay. And then in other areas, you might have a harder rock or something that would help you a little bit.
Places where you don't have that porosity are in some ways less vulnerable, certainly.
Okay. But we like to build our cities all over the world near the sea, it seems. So all of these coastal areas, the largest cities, I believe, in the world are all in coastal areas. How does that business of continued development along the sea, how does that affect this sea level rise? Should we all be running away from this, or should we be continuing to develop as they are in Florida, right on the coast?
So certainly people for generations have lived disproportionately on the coast and close to the coast for a multitude of very good reasons. But certainly that development is something that leaves us with potential vulnerabilities.
Yes.
So risk to sea level rise depends on how high and how fast sea level may rise and what is potentially in the path of that rising sea level. So there are certainly places that are more and less vulnerable, because you perhaps are more vulnerable because projected rise is greater, or because you have concentrations of infrastructure, industry, economic services, housing.
As these hurricanes seem to show that. Which areas of the world seem the most vulnerable at this time? You mentioned our eastern seacoast, so we should be moving New York and Boston and stuff back a wee bit, apparently. What else in the world is in the path?
Locally to us, the East Coast is an area that is potentially at risk for the reasons that it has ongoing subsidence, coupled with what we discussed about the exaggerated sea level rise we would expect to see here if there's a contribution from melting of the West Antarctic ice sheet. The northeast is also somewhat vulnerable to exaggerated rise from ocean dynamics that push water towards the east coast.
I see.
Other vulnerable areas, for example, are low-lying islands in the Pacific,
Yes, yeah.
in part because of the amount of rise they're expected to see, but also in part because of a lack of options to respond, be those economic wealth, the cost of mitigating sea level rise, but the physical restrictions that they have of there is not necessarily any higher land to build on or to retreat to.
Right.
Other vulnerable areas include cities built on large delta systems.
Yes, like in India.
Where they have ongoing subsidence as well. So Southeast Asia, Bangkok, for example, has pronounced subsidence going on, which makes it more vulnerable to future sea level rise.
Right.
You see that also in the Gulf Coast here.
Yeah. Yes.
You know, the Mississippi Delta is subsiding at a very, very high rate, which leads to vulnerability there too.
Right. What's your prediction in terms of what this a lot of people in these areas, what's going to happen and how much time do they have, do you think? I mean, they're not going to be able to just build walls and build walls and build walls, right?
I think we have to decide as a society what our response should be, and I think the role of scientists is to provide the best, most robust projections that we can. And that information should be used in a transparent way for decision making, and it's all about tolerance to risk. And your tolerance to risk is very variable depending on what kind of infrastructure we're talking about. For example, if you're building a beach home that you hope to own perhaps for 20 or 30 years, you have a very different tolerance to that risk than if you're replacing Logan Airport, for example, with a structure that needs to last 100 years and it's being paid for with taxpayer money.
Yeah.
So we need predictions to be at the heart of decision making, I think.
Right. The predictions are there. The scientific community has certainly been forthcoming with the information, but there is resistance at certain governmental levels. What can the scientific community do? Is just put the information out there, get the public revved up? What's the best?
I think the science is always evolving. There's always refinements to predictions being made, and I think one of the major areas of progress recently has been moving away from predictions of how global sea level will change in the year 2100 AD, which has been a big focus of work in the past, to trying to zoom in and talk about how will sea level change in specific locations. What can Boston expect its relative sea level future to look like on time scales that aren't just the end of the century, that put a 2030, 2060, 2070. They're the kind of predictions that I think are of more use to people who are tasked with planning, thinking about future sea level rise, what's at risk, what should we do about it. And I think we are making progress in
certainly
that field.
In some areas, but they're talking 2030, 2050 now, forget 2100, right? That it's happening so fast. Let me ask you quickly about the West Coast. You said there is a difference there, and you've done some work around that. What's the deal with the West Coast?
The West Coast is a very interesting place. Unlike the East Coast, it's a tectonically active coastline. We have a subduction zone.
You mean on the West Coast? Okay.
We have a subduction zone that runs from Northern California all the way up to British Columbia. It's the Cascadia subduction zone. It's the movement of the tectonic plates which produce the Cascade Mountains, Mount Hood, so on. There we have, certainly as someone who considers sea level changes on over hundreds to thousands of years, we have this interesting complication that the accumulation of strain along that subduction zone as one plate is subducted beneath another causes uplift of the land. So as the coast uplifts very slowly, it's a factor that's contributing towards relative sea level fall at those locations. When you have a very large earthquake, that strain is released instantaneously and the land surface drops back to where it once was. That's a very large instant change in relative sea level, perhaps on the order of a meter or even more than a meter that can take place.
rapidly. You mentioned that this fault up like Washington State and northward, they are sort of waiting for an earthquake, have been, and we're talking major earthquake there. Can you tell us anything about that expectation?
So the Cascadia subduction zone we know has the potential to produce a very large magnitude earthquake, by which we mean greater 8 and upwards on the earthquake magnitude scale. So in terms of similar events, we're thinking about events perhaps of a similar magnitude to Indonesia in 2004, Japan in 2011, Alaska 1964, Chile 1960, those kind of events. We know from historical records in Japan, but also from geological evidence on the West Coast, that the last time one of those events took place was in January of 1700 AD. We know from examining the older part of the geological record that those events take place on average about every 300 years, but with a large variability in the recurrence from 100 years perhaps to as much as 1,000 years. So certainly there is a threat to the West Coast from this kind of event. And we actually use sea level reconstructions developed from those coastlines to try and figure out how often these events have happened in the past and perhaps how large they were.
And as you mentioned, it's dramatic. The change is dramatic. It may be accelerating on the East Coast, the sea level rise, but this would be rather dramatic if there was a significant earthquake.
Yeah, in terms of the sea level history of the West Coast, it has all those factors at play that affect us here on the East Coast. We have global sea level rise, we have changes in ocean circulation, we have isostatic adjustment is happening on the West Coast, but it has this added complexity which arises from the earthquake behavior.
I see. Well, now that we've cheered everybody up about this, I've asked you specifically because you have a kind of interdisciplinary approach to your work. This is a very important trend in a number of sciences right now, and I wonder if you'd give us a little idea of how you work in this field.
I was trained as an earth scientist. My work now, I frequently work with biologists and chemists, statisticians, computer scientists, in order to try and maximize the amount of information we can glean from the geological record, but also to think about how this work factors into thinking about the future. And certainly interdisciplinary science is a big part of sea level research, and I think it's a big part of
That's good to know.
Science in general.
Yeah, right. There's very definitely, it seems to be a shift, and especially in terms of dealing with some of these huge issue things that you need many, many specialities. You have done data that is used by the Intergovernmental Panel on Climate Change. Is that the purpose now of this kind of work, is to present this to these international forums?
I think there's, in the broadest sense, there's two motivations for doing this kind of work. The first is very much on the science side, and that's to learn something about process, about how Earth works, and sea level reconstructions can tell us an awful lot about that.
I bet it does.
Depending on where you go, what time period you examine, you can learn things about how viscous Earth's mantle is compared to the frequency of large earthquakes. You can learn about changes in ocean circulation, and they're fascinating things to learn about. They're also useful things to learn about.
Yeah.
The other side of the coin is to try and provide a real tangible benefit to society as a whole, and that benefit comes from revising, constraining predictions of future change.
Do you have any speculation for the future? Will we be okay? Can we deal with the science, with the sea level rise?
One of the encouraging things is if you look at projections of future sea level rise, they are very dependent on which emissions trajectory we follow. Business as usual results in more sea level rise and faster sea level rise, which, all things being equal, will cause more trouble and be harder to avoid the consequences of than less sea level rise.
Right.
Whereas the low emissions scenario do show that the total amount and the rate of sea level rise can be, to to some degree, held back.
Okay.
So we have a decision to make, which emissions pathway we follow, and sea level rise will correspond to that pathway.
A real choice there, as opposed to that you have a CO2 buildup in the air, for example, in the atmosphere. There's very little that can be done about that now. If we stop now, we still have that problem. But if I understand you, you're saying that if we could get things under control, that the sea level rise would be diminished at least that it can, and if we don't get it under control, then it will continue to accelerate.
Absolutely.
Okay.
The more CO2
All
we
right.
put into the atmosphere, the warmer it becomes, the more that sea level will rise.
Okay, all right, for the reasons that you mentioned about the sea expanding and so on.
Certainly we see in projections that as we move forwards in time, we see a greater and greater contribution to sea level rise from melting of land-based ice.
Yes, yes, and my concern is that once that gets started, it doesn't seem like that can reverse too easily.
No, and there is good evidence, certainly from Antarctica especially, that there are thresholds in the system that once crossed,
yes,
will have a positive feedback, a vicious circle,
okay,
which
tipping
will
points.
exaggerate sea level rise.
Okay, all right. I thank you so much for giving us this very valuable information. I wish you well with all your most interesting research. I hope you'll come back and tell us more about some of this other stuff that you do.
Thank you, Yvonne. Thank you for having me.
Thank you.